Swayam Prabha. Digital India. Educated India.
Welcome to the second lesson of the ninth module, which is on stability of columns part 2. In fact, in the last lesson we have introduced the concept of the buckling in a member, a vertical member which is subjected to a compressive force, which we have termed as column, and also we have looked into the stability aspects of different types of column members, and thereby we have introduced the derivations which was proposed by Leonhard Euler, which we normally call as Euler's buckling load formula. Now, in this particular lesson we are going to look into the aspects that where the Euler's load can be applied, or in other words what are the limitations of Euler's critical buckling load in applying in the column members, and subsequently also we will look into what are the other formula that can be used for evaluating the critical load in a column member. Hence, it is expected that once this particular lesson is completed, one should be in a position to understand the limitations of Euler's critical buckling load formula, and also we look into the concept of intermediate columns and evaluation of buckling load using Rankine's formula. Also, one should be in a position to evaluate the critical buckling load in different types of column members. When we talk different types, we mean that the column members having different support conditions, as we have seen in the previous lesson, that the column members can be having the hinged ends, or you can have fixed ends and also fixed and hinged, or combinations of these, and then how do we calculate the critical buckling load in such column members having these different types of supports. The scope of this particular lesson therefore includes the recapitulation of previous lesson. We will look into some aspects of the lesson which we have discussed in the previous class, wherein we have given the concept of the buckling and the stability, and we have discussed the Euler's critical buckling formula. We will look into some more aspects of that. We will look into the limitations of Euler's critical buckling load formula, and also this particular lesson includes this Rankine's critical buckling load for intermediate columns. In fact, we will look into what we really mean by intermediate column and how do we evaluate the critical buckling load using this Rankine's formula, and also we will look into some examples for the evaluation of buckling loads in columns of different support conditions. Well, before we proceed, let us look into the answers to the questions which were posed last time. The first question given was, what is meant by critical buckling load of columns? Now, let us discuss this with respect to the buckling model which I discussed last time in the previous lesson. If you remember, the actual column, supposing if we consider an idealized column which is hinged at both ends, and which is perfectly straight, subjected to axial load. This we can model as having two rigid bars A B and B C, and connected with a spring, rotational spring at point B, the spring stiffness of this rotational spring being beta. Now, and this particular system where A B and B C are perfectly concentric, the axial load P is acting in this member, that is also concentric. Now, if we give lateral load to this or a little disturbance to this kind of system, then it is expected that the bars will move, thereby an angle theta will be made by these bars, and the rotational spring which is provided at B having the stiffness beta will produce a restoring moment, the magnitude of which will be equals to the total rotational angle that these two bars will be undergoing, which is twice 2 theta. This spring is undergoing. So, beta times 2 theta is the restoring moment. If I call that as MR, this is equals to beta times twice theta. Now, if we remove this disturbing load, as we have given a disturbance and brought the columns bar system in this particular form, if we remove that disturbance, it is expected that the bars will come back to its original position, because this restoring moment given by the rotational spring will overpower the effect of this axial load, and thereby this kind of system we call as a stable system, where the restoring moment is larger than the axial load P which is acting on this particular member. Now, as you can see that when this rotational spring is giving a restoring moment, the axial load P is giving opposing action, that means it is trying to increase the movement of the point B, and thereby it tries to create destabilization in the system. Now, supposing if we keep on increasing this load to such an extent that the axial load exceeds the restoring moment capacity, that means the moment produced by this axial load through this movement, if that exceeds the restoring moment capacity, then the system will no longer be in equilibrium position and it will fail, and if we remove the external disturbance, the restoring moment will not be, or the spring will not be in a position to restore back the normal position, and thereby the system becomes unstable. Now, between these two positions, the stable and unstable position, there is a unique value of the load P which we call as the critical load. Now, this is what is stated over here, that the transition between the stable and unstable conditions that occurs at a special value of the axial force, which we term as critical load. In fact, so critical load is that load beyond which if we add a little load to the system will become unstable, or it will fail by excessive deformation or unrestrained deformation, which we call as buckling. So, the member will no longer will be in a stable state, it will become unstable and it will fail. So, that is the load, that is the limiting value of the load beyond which the member fails with little addition of the load, we call that limiting load as the critical load. And as you have seen that last time we had derived for this particular buckling model, that what will be the value of the critical load. Now, as you have seen that the restoring moment is equals to beta times twice theta, the total rotation that it undergoes, and if we take the equilibrium of the forces for this particular free body, as we had seen that the horizontal force is equals to 0. Now, if we take the moment of all the forces with respect to B, we get m minus p times L theta by 2 equals to 0, and thereby since theta equals to 0 will lead to the normal situation, that means there is no movement of the bar, and thereby question of instability does not come in. So, if we put 2 beta minus P L by 2 is equals to 0, that gives us a value of P which is equals to 4 beta by L. Now, this value of P becomes critical when this matches the restoring moment M. Now, as soon as in this particular state, if we add additional load over here delta P, then the system is going to collapse, and that is the reason this load is called as the critical load PCR. Now, let us look into the other questions. Now, the second question given was how will you evaluate the critical compressive stress in a column member. Now, that we have discussed about the critical load, that a column member subjected to axial load, so when it reaches to the criticality. So, what is the corresponding critical compressive load? Now, what we are interested in, as you have seen earlier, that if we like to evaluate the stress corresponding to that critical load, then what is the which we term generally as critical compressive load, how do you compute that? And the third question what is given is what is meant by slenderness ratio. In fact, I would like to answer these two questions together, both the second and third questions simultaneously. Let us look into the formula which we had derived or which was given by Leonhard Euler, that the PCR, the P critical is equals to pi square E I over L suffix E square, what L suffix E we mean is by the effective length, as you had seen last time that we had discussed what we mean by effective length, because for different support conditions we will have different values of this LE, and this is what we call as the critical load. Now, if we replace this I, the moment of inertia, in terms of the cross sectional area, then I is equals to A r square, where r is known as the radius of gyration of the section. So, if we replace I with A r square, then and divide the whole of equation by cross sectional area A, then we get on the left hand side that P C r by A, which we term as the critical stress sigma C r. This is equals to pi square E divided by, if we take r down, it becomes L E by r square. So, the expression for the critical compressive stress, the P C r, as you had seen that P by A is the compressive stress, the normal stress. So, here we call, since we are computing the stress corresponding to the critical load P C r, we call this as sigma C r, the critical compressive stress, and critical compressive stress sigma C r is equals to pi square E divided by L E by r square, and this term L E by r we call as slenderness ratio. So, you see from these two expressions we are getting two terms, one we call as the sigma C r, the critical compressive stress, the another term which is emerging out is the effective length L E by r ratio, and this particular ratio we call it as slenderness ratio. It indicates that how slender or how long the member is with reference to its cross sectional area. Now, this is what is indicated over here, that L E by r is the slenderness ratio and sigma C r is the critical compressive stress. Now, if you notice it carefully, that when the value of L E by r will be larger, then the value of compressive stress sigma C r will be less, and larger L E by r means the lower value of r, or in other words what I can tell you is that if we have a cross section for which you have a smaller value of r, thereby you will have larger value of L E by r, and thereby that will give you the minimum possible stress. So, if you have a section which is unsymmetrical, say for example, if we have a rectangular cross section and the moment of inertia about the both axes I x x and y y are different, then the, since r is nothing but equals to root of I by a, the lower the value of the moment of inertia, lower will be the value of r. So, the moment of inertia about y axis in this particular section will be lower. So, r y is going to give us the lower value out of the two r values. Now, so minimum of this r will give us the value of larger L E by r, and thereby we will have lower the stress, and that is what is the critical stress. So, if you have a cross section wherein you have different values of the moment of inertia about two rectangular axis system x and y, and thereby we must deal with the minimum value of the radius of gyration, so that you get critical value of the slenderness ratio, which is L E by r, which is larger. And as we are looking into it here, the larger the value of the slenderness ratio, smaller will be the stress, and thereby if you consider that particular stress with the cross sectional area, that will give you the load carrying capacity of the member. So, we will have to always look for that what is the minimum possible stress that will be required, otherwise the member will fail by buckling if we do not, if we go beyond that particular load. So, this is what is important when we talk about the stresses, that slenderness ratio L E by r and the critical compressive stress sigma C r. Well, having looked into these questions, let us once again look back to the values of the critical load that we had evaluated or which was derived by Leonhard Euler for different column support conditions. Now, first one, which was an idealized column member we had considered, wherein the ends of the column members were hinged, and that is what we have put it as the hinged end. And as we had seen, the Euler's critical load corresponding to this kind of column having length L is equals to pi square E I over L square. Now, when the support condition changes, say the lower becomes fixed and the top become free, which is that of a cantilever member. This kind of members we call as cantilever members, as we have seen in beams. Now, here the condition is fixed free condition, and the Euler's critical buckling load which we get corresponding to this is equals to PCR as pi square E I over 4 L square. Now, since here we have the coefficient of L as 1, now if we try to write down everything in as equivalent to this, then we can write that as PCR as equals to pi square E I over 4 L square. This we can write as pi square E I over let us say 2 L square, and this parameter 2 L we call as equivalent to the single length L, which is L E. So, in the first case, as you can see that P critical is equals to pi square E I by, let me add a term, let us say k times L square, where k times L is the effective length L E. Now, in the first case k is equals to 1, in the second case as you can see k is equals to 2. So, the effective length L E is equals to twice the L, and the value of k is equals to 2. Here the value of k is equals to 1, here the value of k is equals to 2, where k we call as the effective length coefficient. That means, we add this factor or the coefficient to the actual length to get the effective length of the member. So, likewise, if we compute the critical load for the other two cases, like you have fixed hinged and fixed cases, then for the fixed and hinged condition, one end fixed other end hinged, we get the critical load PCR as equals to twice pi square E I over L square, and this if we write in terms of pi square E I divided by, we can write this as L by root 2 square. So, here the value of k is equals to 1 by root 2, which is equals to 0.707, and that is what has been written over here, that L E is equals to 0.7 L. So, value of k here is 0.7, and if we consider a case where the supports are fixed at both ends, the column member is fixed at both ends, then the critical load which we get is equals to 4 pi square E I over L square, and thereby we can write P C R as equals to pi square E I by L by 2 square, and thereby k is equals to half over here, and that is what is indicated, that effective length is 0.5 times L. So, k is equals to 0.5. So, you see that we get different values of the k or the coefficient of the effective length, based on which we can compute the value of the critical compressive load for each of such column members. And as we have seen now, that once we can evaluate the critical compressive load, correspondingly we can evaluate the value of the critical compressive stress as well. Now, having looked into this, let us look into the variation of these stresses and the assumptions with which this Euler's formula were derived. Now, you see when we had derived, or the formula which was proposed by Leonhard Euler, it was assumed that the column member is perfectly straight. That means, we had considered an idealized situation, that the column member is perfectly straight and subjected to a compressive load which is truly axial. That means, it is passing through the centroidal line of the cross sectional member of the column member. So, the column is initially straight, the load is truly axial, and the material is homogeneous and isotropic, and it behaves elastically up to the critical load. So, up to the limit of the critical load, we presume that the material behaves in an elastic manner, and thereby the Hooke's law is applicable. So, beyond critical load, there might be inelastic deformation, or the beyond buckling, when the buckling occurs, the failure subsequently could be in an inelastic manner, which is of course not in the scope of this particular lesson. Now, if you look into the Euler's critical buckling load formula, you will observe that we had the P critical as equals to pi square E I over L E square. Now, we are talking about the critical load, that means how much load a member can carry. So, which must be related to the strength of the column, but unfortunately we do not have any parameter in this particular expression which signifies the strength of the member. Instead, what we have is the elastic modulus E only, which is the material characteristics present in this particular expression, and this is what is written over here. You see that Euler's critical load formula is used in connection with the strength of the column, but the formula does not contain any variable related to the strength of the material, and this is what is very important. And so, the only property that is involved in this particular expression is E, which is the elastic modulus of this material that we are using. Well, now with this background, if we look into the variation of the critical stress with the slenderness ratio L E by R, you will find as we have discussed in this particular section that sigma C r is equals to pi square E divided by L E by R square, where sigma C r is the critical stress and L E by R we have designated as slenderness ratio. Now, as I was telling you that if this value of the slenderness ratio increases, then the value of the sigma C r decreases. Now, if the L E by R value becomes lower and lower, that means the stress level will be higher and higher. Now, what does that imply? That means, if you have a very small L E by R or very small value of the slenderness ratio, you will have very high value of the stress. But what does that physically mean? Now, supposing if you have a stress which is much higher than the yield stress of the material, then what is going to happen? The material is going to fail as soon as it crosses the yield stress. So, the stress value higher than yield stress makes no sense. So, what happens is, if we are talking about a column where the slenderness ratio is very low, or as we have seen that in case of short columns, the critical stress is thereby is the yield stress. The yield stress is the critical value, because once the member reaches to the yield stress, the material is going to yield, and as we have noticed earlier, as we have discussed earlier, that for a short column, when it is subjected to axial load, or even if the load is eccentric, thereby it is going to give you the axial load and the bending, and in terms of the combined stresses, if we compute the normal and the bending stresses in the member, as soon as the stress level goes beyond the yield stress, the member is going to fail by crushing. That means, the material will yield, and the question of buckling will not arise in that particular situation. So, this Euler's critical load formula has a limitation that beyond a certain value of L E by R, we cannot use this Euler's critical buckling load formula. Now, if we consider the material as a steel material, for which we know that the proportional limit stress, the sigma P L is equals to 210 megapascal, and the yield stress, say if we consider as 250 megapascal, then if we consider that proportional limiting stress, which is as equals to 210 megapascal, then we get a value of slenderness ratio L E by R as equals to 97. Now, this indicates that if we use the slenderness value less than 97, then the stress level is going to go beyond the proportional limit. And as you have noticed that if the stress level goes beyond the value of sigma y, then the material is going to fail by crushing, and which is the criteria that for a short column. Hence, there is a limiting value for the slenderness beyond which the Euler's critical load formula is applicable, otherwise it is not applicable for such type of members. So, in this particular curve, as you can see, where sigma C r is plotted against the slenderness ratio L E by R, there is the limiting value of the slenderness, and this curve the Euler's curve is valid when L E by R is greater than this limiting value. when LE by R is higher, let us call this LE by R as the limiting value. This is the LE by R which we have computed for steel, and let us call that this LE by R as the limiting value. Now, when actual LE by R in the member is greater than the limiting value of the slenderness ratio, then we can use the Euler's critical load formula. But if it is less than this value, if actual LE by R is less than the limiting LE by R value, then we cannot use the Euler's column buckling formula. So, what happens is, you see that we are getting clearly two areas. One is that beyond the limiting LE by R or the slenderness ratio, or higher the value of the limiting value, we can go for the Euler's critical load buckling formula, load formula, based on which we can compute the critical load in the member. And the other aspect is that, as we can see, that when the stress goes beyond the yield stress, the material is going to fail by yielding. So, for the short columns, when sigma y is the critical stress, we can evaluate what will be the load carrying capacity. So, between these two cases, that you have a short column where the member is going to fail by yielding, and a long column formula where beyond a limiting value of the slenderness ratio, we are using Euler's column buckling formula. Now, in between these two, there could be some members which may fail in the combination of buckling and yielding, and those members which are in between this short column and long column, we call them as intermediate columns. And as you have noticed that intermediate columns will have L by R less than the limiting value of L by R or LE by R, and thereby we will not be in a position to apply Euler's critical load buckling load formula for evaluating the critical compressive load for such members. Now, for such intermediate members, we use different formula. In fact, there is a formula which was proposed by Rankine, and we call that as a Rankine's formula for evaluating the critical load in intermediate columns. So, for both short columns and intermediate columns, in fact, the Euler's Euler's formula will not be applicable, and it will not give you the appropriate results. Now, let us look into this Rankine's formula, which was proposed by Rankine, which we commonly call as Rankine-Gordon formula. Now, these are applicable for the intermediate columns, and Rankine suggested that an empirical relationship for evaluating buckling load in this form, which is which reads as 1 by PR is equals to 1 by PS plus 1 by PE, where PR is termed as the Rankine's buckling load, PS is the direct compressive load, which is equals to the yield stress multiplied by the area, and PE is the Euler's critical buckling load formula or buckling load. So, we have three terms PR, PS and PE. PR is the critical buckling load that is given by Rankine, and that is what we are interested to evaluate, and that is being evaluated in terms of PS and PE. PS is the load which is evaluated from the direct compressive stress, and that is for the short column, and as you know, for the short column the critical compressive stress is nothing but the yield stress sigma y. So, this particular expression, that 1 by PR is equals to 1 by PS plus 1 by PE, if we evaluate this comes as PR is equals to PS multiplied by PE by PS plus PE, and then if we divide the denominator and the numerator by PE, we get this as PS by 1 plus PS by PE, and as I said that PS is the direct compressive load, which is equals to the yield stress sigma y times the cross sectional area A. So, PS is equals to sigma y times A, and PE as you know, there is the Euler's critical buckling load, which is equals to pi square E I over L E square. So, that is what is substituted over here, and replacing I replacing the I over here in the Euler's critical load formula, I as A r square, we get this as P r is equals to sigma y times A by 1 plus sigma y by pi square E times L E by r square. Now, here this sigma y by pi square E, which is dependent on that material, the yield stress of the material and the modulus of elasticity of the material is commonly termed as Rankine's constant. And again, as you can see that the critical load for the member will be dependent on this LE by R, the slenderness ratio, and the critical stress corresponding to or the yield stress of the material. So, this is the expression which was proposed by Rankine for evaluating the critical buckling load for the intermediate column members. So, now as you have seen, the clearly we have three distinct areas. One we have called as short column, another we have called as long column, and now we have defined another column range which is between short column and the long column. For the long column members, we can use Euler's critical buckling load formula for evaluating the critical compressive load when the actual slenderness ratio LE by R ratio of the member exceeds the limiting slenderness value. As we have just now seen, for any material we can compute LE by R limiting for a particular material, and when a column member is made up of that material, if we know the actual slenderness, when that actual slenderness exceeds the limiting value, we can use the Euler's column formula for evaluating the critical load. Or if the actual LE by R is much less than the limiting LE by R value, wherein the failure will be governed mainly by the yielding of the material, and wherein we take the critical compressive stress as the yield stress of the material, that multiplied by the cross sectional area will give the critical load in as that of a short column. And in between these two, where the members could fail in the combination of the crushing or yielding and the buckling, those types of columns we call as intermediate column, and we can evaluate the critical buckling load of those columns using Rankine's formula. Now, having looked into this with this background, let us look into some of the examples. In fact, this particular example I had given to you last time and asked you to look into. Let me give you the solution for this. Now, this is a column which is hinged at both ends, and the length of the column member is 3 meter. Now, the cross section of this column is a rectangular one having a size of 150 millimeter by 200 millimeter. Now, it says that this particular member carries a load of 300 kilonewton. You will have to determine whether this particular section, the cross section of 200 millimeter by 150 millimeter, will be able to carry this load, this 300 kilonewton load, if a factor of safety of 3 is to be used for this purpose. Now, you see, when we use a factor of safety of 3, it means that if a member is subjected to a load of P, we should check the stress in such a way that it can withstand a load of 3 times P. That is the meaning of that factor of safety of 3. So, the section is to be chosen, or the stress has to be evaluated in such a way that it can withstand a load of 3 times P, and then only we can apply a load P, and we say that the factor of safety applied to this member is 3. So, we will have to check whether the member can withstand a load of 300 times 3 as 900 kilonewton. Now, let us look into this. If we compute the value of the critical load using Euler's critical buckling load formula, you see that value of the IY. Now, as I was telling you, the cross section is a rectangular one, 150 by 200, and the rectangular axis system of this is XX and YY. Now, which can compute the moment of inertia of this section IX and IY, and as you know, IX will be equals to 150 times 200 cube divided by 12, and IY will be equals to 200 times 150 cube by 12. Now, clearly from this expression you can see that the value of Ix will be higher than Iy, and as you know that the value of R is equals to root of I by A, and for this particular section we will have two values of R, which is Rx and Ry, and Rx will be equals to root of Ix by the cross sectional area, and Ry will be equals to Iy by the cross sectional area. Now, since Iy is less than Ix, so expectedly Ry will be less than Rx. So, we compute I y, which is going to give us the minimum possible value, because beyond that, if we apply load beyond that, it is expected that it will buckle about the y axis. And as I had shown you last time, that if you take a member and apply a compressive load, if the member is a slender one, is a long one, then it buckles about one of the axis, and obviously it is going to buckle about the axis which is weaker if the two axes do not have the same the strength, like if we do not have the same moment of inertia about both the axes, or in other words the section is not a square one as we are dealing with in this particular case. Since it is a rectangular one of the moment of inertia is less in comparison to the other one. So, it is weaker about y axis in comparison to the x axis, and therefore, it is going to buckle about y axis. Now, as I had shown you last time, or the derivations we have looked into, we have considered the buckling of the member in one direction, that means, we have taken in the positive y direction. Now, the question is, the buckling can physically occur in this direction or it can occur in this direction. Now, whichever direction it occurs, our evaluation will also be the same. The expression for the critical load will have unchanged. Now, this we had considered because of the our positive axis direction. Now, so if we apply the critical load formula given by Euler, then we get a load value as equals to 771 kilonewton. E is given as this is pi square, and E, as we have seen over here, is 56.25 into 10 to the power 6 is the I, and E is given as 12.5 into 10 to the power 3. So, and L is equals to 3000. Now, since this is this column member is hinged at both ends, so the L E is equals to K times L, and K in this particular case is equals to 1, and that is what is indicated over here. And if we evaluate this, we are going to get a value of P critical as equals to 771 kilonewton. Now, as I was telling you that we will have to apply a factor of safety of 3 to this particular member, and thereby to have a 300 kilonewton load on this column member, we will have to check the section for a load P as equals to 3 times 300, which is equals to 900 kilonewton. Now, since we find that using Euler's critical load formula, the critical load is 771 kilonewton, which is less than 900 kilonewton, then this particular section will not be appropriate to apply a load of 300 kilonewton with a factor of safety of 3. So, to fulfill these two aspects, that means, we will have to apply a load of 300 kilonewton with a factor of safety 3 will not be appropriate for this section, or this section will not be able to carry that load. Now, if you have to satisfy that, that means, you will have to have 300 kilonewton load on the member with a factor of safety of 3, naturally then you will have to change the cross sectional area, you will have to go for higher cross sectional area, so that you can satisfy this particular criteria. Well, let us look into another example, and this particular example is a steel column of length 4 meter, and the ends of this particular column is fixed, both the ends are fixed. Now, what is the minimum length of the column for Euler's formula to be applicable? Now, first of all, we will have to find out, though it is given that the length of the column member is 4 meter. Now, we will have to find out the length for which we can apply the Euler's critical load formula for such situation, and the member properties given are E of this is 200 GPa, the gigapascal. The stress at the proportionality limit is equals to 200 megapascal. The yield stress of the material is 250 megapascal, and the values of the radius of gyration about x and y axis, r x is 180 and r y is 30 millimeter, as it is expected that the moment of inertia about y axis is less than the moment of inertia about x axis, and thereby the value of the radius of gyration about y axis is less than the radius of gyration about x axis, and the value of the moment of inertia about y axis is given, the cross sectional area of this particular member is given. Now, the question is, let us first find out that what is the value of the limiting length up to which the Euler's critical buckling load formula can be applied. Now, the value of E is given as 200 GPa, the stress at the proportionality limit is given as 200 megapascal. Now, from the critical stress expression, that sigma CR is equals to pi square E by L E by R square, as we have seen right now. From this we can write that L E by R square, R of course, we have taken R minimum, which is 30. This is equals to pi square E is given as 200 gigapascal times 10 to the power 3, so much of megapascal divided by 200 megapascal. So, this gives us a value of the length L E as equals to 2.98 meter. So, that means, this is the minimum length that is needed for the member, so that we can apply the Euler's critical buckling load formula, and mind that this is the effective length L E. Now, here the member which we have considered is a fixed ended member, and thereby as we have seen that the value of K for fixed ended member is equals to 2, because for a fixed ended member the critical load is equals to 4 pi square E I by L square, and thereby the L by it becomes L by 2. So, the K value becomes half. So, K with K as 0.5, and for 4 meter the length here is going to be equals to 2 meters. So, effective length then in this particular case is equals to 2 meter, and this being less than the length, the minimum length we need. So, thereby we cannot apply the Euler's critical buckling load formula. So, as you can see that limiting L E by R, that means this length divided by the minimum R is 30, if we use the L E by R we get as 99, and the actual L E by R, that means 2000 divided by 30 is the actual value of the L E by R. L E here is 2000, which is 0.5 times 4000, and this is equals to 67. Now, this value is less than the limiting L E by R value, and therefore, Euler's critical load formula will not give us the value of the critical load. So, the options what we have is to look into that if this member fails by the yielding, that means it reaches to the yield stress value, then the value of the critical load will be the yield stress multiplied by the cross sectional area, which gives us a load of 2318 kilonewton. Now, if we consider this as in the intermediate range, that means it may fail in combination of the buckling and the yielding. No, neither in the buckling range, because we cannot apply the Euler's load formula, and on the short column range where it goes to the yielding, that is sigma y times A, that is the other limiting value. Now, if we consider that it fails in the combination of the buckling and the yielding, then it comes in the category of intermediate column, and let us look into that what is the critical load we get if we use Rankine's formula for evaluating the critical load. Now, the critical load which we get corresponding to the Rankine's formula, which is given as sigma y times A divided by 1 plus sigma y by pi square E times L E by R square. Now, sigma y the yield stress given is 250 megapascal, 9272 is the area of the cross section. Then we have 1 plus 250 again is the sigma y, pi square E is 2 into 10 to the power 5, and L E by R value is equals to 2000 by 30 square. Now, this gives us a value of 1483 kilonewton. Now, as you can see that if we go up to the yield stress level or up to the crushing level, then the load which we can apply is this. And if we consider that the column might fail, since the L by R value which we have got, the actual L by R we have obtained less than the limiting value, there is a possibility that the member is going to fail in the combination of the buckling and the yielding, and thereby we need to limit ourselves to a load of 1483. So, the maximum load that we can apply is equals to 1483. So, that the member does not fail either by buckling or by yielding or in combinations of the two. Now, so this is the limiting load in this particular case. So, for this particular member, as it has been said that what is the minimum length of the column for Euler's formula to be applicable, which we have seen as 2.98 meter, and mind that that is the effective length 2.98 meter. So, in this particular case, since it is fixed ended column, and as we have seen for a fixed ended column member, the value of the effective length coefficient is half. So, that means you will have to have a length column length of 2.98 times 2, that means around 6 meters length you need for a fixed ended column member, where we can apply the Euler's column buckling formula, or else we will have to go for the either the short column formula, which is the yield stress multiplied by the area, or by the Rankine's formula, which is that for the intermediate column. Now, let us look into another example problem, wherein this particular member is having a cross section of that of a tube. So, it is a tubular member which is subjected to a compressive load, and this particular member is hinged at both ends. That means, this is an hinged column, for which we have seen that P critical is equals to pi square E I over L square, and thereby the coefficient k is equals to 1, the effective length coefficient is equals to 1. Now, here you will have to compute the critical load using both Euler's and Rankine formula. So, we will have to find out the value of the critical load that this member can carry using both Euler and Rankine formula, and the value of the yield stress given as 300 megapascal, and the value of E is equals to 2 into 10 to the power 5 megapascal. So, let us look into that what will be the critical LE by R. So, this being a tubular member, as you know that if we compute the value of the moment of inertia and the cross sectional area will be pi by 4 times d outer square minus d inner square, and the moment of inertia will be the pi by 64 times d outer square minus d inner square to the power 4. So, let us look into those values. You see, this is the value of the moment of inertia, which is pi by 64 times d outer to the power 4 minus d inner to the power 4. This gives us a value of 8.59 into 10 to the power 4 millimeter to the power 4, and the area is equals to pi d square by 4, which is d outer square minus d inner square, and this gives us an area of 549.8 millimeter square. Now, if we compute the value of the radius of gyration r, which is equals to root of I by a, this gives us a value of 12.5 millimeter. Now, if we compute the limiting value of the LE by R, which is equals to root of pi square E by sigma CR, which is the critical stress, and critical stress here the yield stress given is 300 megapascal, and value of E is 200 gigapascal or 2 into 10 to the power 5 megapascal. This gives us a value of L by R as 81. So, this is the limiting value of the slenderness ratio LE by R, and what is the actual LE by R in this particular case? Now, the length of the member which is given over here is 2 meter. Sorry, this is 2.5 meter, as it is written over here, it is a 2.5 meter, and this is hinged at both ends. So, L is equals to L, or K is equals to 1 in this particular case. So, yeah, we have used a value of 2500. So, if we compute now the value actual LE by R, if we divide this by 12.5, we get the value of actual LE by R as 200. Now, since this actual LE by R is higher than the limiting LE by R, so we can apply Euler's critical buckling load formula for evaluating the critical load in the member. So, we have used Euler loads, which is pi square E I over L square, which gives us that pi square E is 2 into 10 to the power 5, I is 8.59 into 10 to the power 4, and LE is 2500 because K is equals to 1. So, this gives us a value of 27.13 kilonewton if we use Euler's critical buckling load formula. Now, if we use Rankine's critical buckling load formula, then we get sigma y again here is given as 300, length is 2500, cross sectional area as we have computed as equals to 549.8 millimeter square, then and E is 2 into 10 to the power 5, we get a value of 23.3 kilonewton. Now, you see that we have now two values of the critical load, one is corresponding to the Euler's critical buckling load and another one is corresponding to the Rankine's critical buckling load. Now, since we have tested that in this particular case the value of the actual slenderness ratio LE by R is higher than much higher than the limiting value, hence the stress level will be much lower, as we have seen in the critical stress versus the slenderness ratio curve, that if you have a larger value of the slenderness ratio, then the corresponding stress is much lower than the yield stress, and thereby the failure which will be dominated in such columns will be more in terms of buckling rather than the going for the yielding. Hence, here since the LE by R value or LE by R ratio which much higher than the actual or the limiting LE by R. So, we can use the Euler's formula or Euler's critical load we can take as a guiding critical load for the member. So, the critical load for this member will be 27.13 kilonewton. Now, here in this particular example as it is shown over here, the length of the member is 2.5 and this is a mistake, this is not 2 meter, this is 2.5 meter. Well, let us look into another example wherein we have a member which is made out of timber, the cross section of which is a 50 millimeter by 100 millimeter rectangular one, and the length of the member is 1.2 meter. Now, this particular member is used as a cantilever column. The value of E is given as 10 GPa, 10 gigapascal, and the stress at the proportionality limit is 30 megapascal. We will have to determine the largest axial load that this member can carry with a factor of safety of 2. Now, if you look into that the cross section of this member is a rectangular one having size 50 millimeter by 100 millimeter, the length of the member is 1.2 meter and this is a cantilever column. Now, the meaning of cantilever column is that it is fixed at one end and the free at the other, and this is subjected to a compressive load P. So, we will have to find out that how much load P we can apply to this particular member having this particular section, so that we can have a factor of safety of 2. You keep this aspect in mind that we will have to impose a factor of safety of 2 and we will have to decide about that what load P we can apply on this member. Now, if we look into the cross section of this, as we have seen earlier for these rectangular cases, you have the x and the y are the two rectangular axis system, and the width of the member let us consider as 50 and depth as 100 millimeter. And so, we can compute the value of I x and I y, and as you know I x will be equals to 50 times 100 cube by 12 and I y will be 100 times 50 cube by 12, and since I y will be less than I x. So, thereby R y will be less than R x for this particular section. Now, if we compute the value of the R y which is equals to root of I by a, I y by a, and I y as I said is equals to 100 times 50 cube by 12 and area is equals to 50 times 100. So, the value of R y comes as 14.43 millimeter. Now, for this if we compute the value of the length of the member is equals to 1.2 meter, and since this is a cantilever member, we have seen that for a cantilever pi the critical load is equals to pi square E I over 4 L square. So, thereby this is equals to pi square E I divided by 2 L square, and 2 is the value of k, which is the effective length coefficient. Now, so this twice L, as we have called it as LE. So, k becomes 2. So, L is given as 1.2 meter, thereby the effective length is 2400, and that is what is indicated over here, that P critical which we use is equals to pi square E I by L E square. Now, E here is 10 gigapascal. So, 10 into 10 to the power 3 megapascal, I is 100 into 50 cube and by 12 and 2400 square. So, this gives us a value of 214.2 kilonewton. Now, as it has been indicated that you will have to find the load in terms of a factor of safety of 2. That means, you will have to apply a load P in such a way that you can achieve the factor of safety of 2. That means, if we apply a load of twice P, the member should be in a position to withstand that stress. So, the maximum load that should be applied or the should be limited to is half the actual load, because this critical load which we compute from Euler's critical load formula is not with any factor of safety. So, we will have to impose the factor of safety to this. So, if we divide this load by 2, the factor of safety value, the load comes as 107.1 kilonewton. So, the maximum load that you can apply on this particular member is equals to 107.1 kilonewton. Now, if we apply a load higher than this 107.1, then you will find that the member may fail by buckling, but the question is that we have applied a factor of safety of 2. So, in this particular case, even if we exceed by this, it may not fail immediately, unless we have some other effect on this member which can cause the failure of the member. Well, then to summarize, in this particular lesson we have looked into some aspects of the previous lesson. We have as we have seen in the previous lesson, we have discussed about the Euler's critical buckling load formula, and in this particular lesson we have seen what are the limitations of Euler's critical buckling load formula, and also what are the different values of the k, or which we have termed as the coefficient of the effective length for different support conditions of the member, and which are either 1 or 2 or 0.7 or 0.5 depending on the different support conditions we have. Also, we have looked into the concept of critical compressive stress in column members. We have discussed about the Rankine's formula of critical buckling load, which are applicable for intermediate columns, and we have looked into some examples for evaluating critical loads in different types of columns. Now, with this lesson we come to the concluding part of this particular module, which is on stability of columns. Stability of columns, basically we had 2 lessons. In the previous lesson we had introduced the concept of the stability, the buckling, and thereby we had discussed about the Euler's critical load formula which are applicable for the columns, and in this particular lesson we have looked into that what are the different phases of the column, the short column, the long column and the intermediate columns, and then the critical load corresponding to the intermediate column, and then we have looked into the formula which is applicable for evaluating the critical load in intermediate column, which is that given by the Rankine. Now, these are the 2 lessons which we had, and consequently we had looked into some examples which can be evaluated using these formulae. Now, the questions set for you are this, that what is the effective length of a cantilever column, what is intermediate column and how is it different from long or a short column, and what is Rankine constant, it is dependent on which parameters. Well, look into this, you will get the answers in this 2 lessons itself. The answers for this will be given in the next lesson. Thank you.